Hello, I am Seppo Niemi-Colvin, currently based at the Rennie Institute with particularly the Erdős Center, and I'm going to be talking to you today about knot lattice homotopy and the surgery formula. In particular, the main result that I have been working on is that there exists a surgery formula for that knot lattice homotopy that gives information about the dual knot as a doubly filtered space with the evaluative data. It's okay if you do not understand all of those pieces yet. The focus of this talk is going to be explaining what types of objects we are talking about and some context for why those are interesting. So particularly, we're going to start with knot Floer homology because that's a big part of the context for why knot lattice homotopy is a thing. And then zoom in particularly to Floer homotopy, where we start adding those more homotopical notions into the picture before telling you what knot lattice homotopy is. In all of these sections, I'll really be pointing out the opportunities and challenges that each new part brings in, especially so that you can see how each piece is building off the opportunities and challenges from the previous piece. So even if other talks have talked some about knot Floer, we're really going to still dive into what it means in this context. Then in the next talk, I'm going to be focusing more on the surgery formula piece. What is a surgery formula? What do we want out of one? And then what is required to upgrade the surgery formula to include this new information? So let's talk some more about knot Floer homology, which also has a corresponding three-manifold invariant called Heegard-Floer. Knot Floer, some of the opportunities it comes with is that it is a functorial TQT-esque theory, which helps us provide obstructions to certain cobordisms existing. So in particular, we have a category based off of cobordisms, and then that will be going to various other categories, which for now I'm representing with D. And if we understand, if we can say that a cobordism having certain properties, such as being a concordance having genus 0, for example, implies that the morphism we get also has certain properties, then we can figure out how to obstruct those morphisms from existing between two objects in this category. And I'll note that with this setup, one way that technicalities enter the picture, and Heegard-Floer and knot Floer do have lots of technicalities that make things difficult in lots of other small ways. One way is that technically we need to decorate all of our cobordisms here. So I'm going to put a tilde to say that technically we have to have more information here. One way this happens, and will be mentioned through various points, is through spin C structures. Those are like second cohomology classes. However, my focus for this talk is really going to be on the codomain of this functor. And so I'm going to be putting a lot of those technical details in gray to really help us emphasize this other side of the picture. Furthermore, decorations always exist. It's always possible to decorate these cobordisms. So if you're just trying to obstruct a cobordism from existing, the obstructions still apply. It's mainly you might get multiple different morphisms from a single underlying cobordism due to different ways of decorating that cobordism. Furthermore, in order for this to really be useful, or one way that knot Floer makes this really useful, is not only do we have ways to get obstructions based on the structure in D, but we have tools for computation. So we have ways to show those obstructions actually happen. And in particular, if we had a way to obstruct morphisms between objects here, but we couldn't compute what objects we were actually getting, we would have no way of knowing if those objects were hit by this functor, or if we were interested in a particular knot or a particular three-manifold. Do those obstructions apply? And another reason these tools for computation we have, which include things like the surgery formula we'll get more into in the second talk, are really useful, is that even as a part of the challenges, even though we have those tools for general, if we want to compute based off of the definition, well, the definition often involves things like counting pseudo-holomorphic curves, which isn't easy to do directly. Think like singular homology can be great and powerful, but we generally do not compute directly from the definition of singular homology. We have tools like Meyer via torus to make those computations feasible. So let's now dive a little more to like what categories we're actually getting for Haggard-Floer and not Floer. So Haggard-Floer homology is a functor on the pointed spin C cobordism category. As I said, this stuff often grades decorations that you can push to the back. And it lands in graded F adjoin U chain complexes, and which are considered up to homotopy. F is in particular going to be the field of two elements, Z mod 2Z, and U has grading -2. And I'll sometimes re-mention this for emphasis, but unless otherwise stated, and we're really not going to otherwise state, in this context, what I am going to be assuming that our three manifolds are rational homology spheres. It's needed for certain grading stuff to work out. And in this context, morphisms have grading shifts controlled by the geometry. So if you want to control the geometry you're going to allow, you then get that your controls on what grading shifts these morphisms can have. In the middle, I have a graphic representation of a morphism in this category, which will be a four-dimensional compact manifold with the boundary split into an incoming and outgoing end. Everything is oriented, and in fact, everything has these spin Z structures. Those declarations have to restrict appropriately at the ends, and then you get these F adjoin U graded chain complexes and a morphism between them based off of all this data. As an example, here we have two different chain complexes, and which I'm representing as here, there's just a single generator over F adjoin U in grading 0. Down here, we have 3 generators here with the gradings marked. And the differential of B is U times A plus U times C. And then we have this map here. And this is something that actually does come up in examples from Haggard-Floer. Not Floer, we have the functor on doubly pointed knots and cobordisms. Everything has spin C structures. The doubly pointedness gives extra weird decorations, but as I said, we're not as focused on those now. And it lands in bigraded F adjoin UV chain complexes considered up to homotopy. F, as before, is the field with 2 elements, or Z mod 2Z. U, the grading of U is -2, 0, and the grading of V is 0, -2. And from this setup over here, where we have now knots and surfaces interpolating between them with our cobordisms, we get a F adjoin UV linear chain map between 2 bigraded F adjoin UV chain complexes. For example, this thing that looks similar to what we had before, but this time one side is one of the coefficients for B has a U, this particular A in the differential, and C in the differential has a V instead, which matches with the gradings I mentioned earlier. Moreover, in this example, this map we have does have a grading shift involved, which signifies that it has to have some more geometry behind it, and for example, cannot come from a concordance. So now that we have basics version of Floer, one of our goals is to add more structure to the codomain to hopefully get more obstructions. And some ways that already has happened is that invariance does work over Z adjoin U or Z adjoin UV, though naturality currently only works up to sign. Naturality is basically a more restrictive, well-definedness idea than invariance. Furthermore, there's a symmetry in the theory of Haggard-Fleur, which paired with first-order naturality statements for f adjoin u, gives us a homotopy involution that interacts with the decorations in a regular way. A similar symmetry for not-Fleur gives iota k, often called the knot involution, which is almost a homotopy involution. Almost, in particular, it will swap u and v, and it's going to square to the identity plus another term that is well understood. So it is not always an involution, but it is close enough that it is still called the knot involution. These involutions are what I mean when I talk about involutive data. And these involutions have especially led to more obstructions to concordances and homology cobordisms. For example, it's with the three-manifold involution that we were able to show that the homology cobordism group, integer homology three spheres, modulo homology cobordisms that look like cylinders under homology with operation connect sum, that group has a z infinity summand. So now let's move on to talk about Fleur homotopy. Given a chain complex of free abelian groups, we'll come back to U later, and we'll assume it has a preferred basis, which our constructions for chain complexes do have these preferred bases. One way when we could add more structure is if it were the cellular homology of a CW complex. In particular, this chain complex could be S2 wedge S4, or it could be CP2. And if you could make those choices, you would have more structure on your situation. And furthermore, we want to do it not just like in a specific case, but if we have a functor from a category to chain complexes or the derived chain complexes up to homotopy, then we might want to factor that whole functor up to topological spaces. So that way we go back to how we construct our functor and go, was there any information we threw away that we could still remember and use to give more structure? And I'll say one note here, this ability to factor is not guaranteed for an individual chain complex, nor is it guaranteed for a whole theory. You have to be, particularly for a whole theory, you need to be able to show that you made those decisions in a consistent way for different representations of the same knot or three manifold. And also, if you're interested in the broader Fleur homotopy picture, you probably are going to be working with pointed CW complexes and reduced cellular homology, and also spectra rather than spaces. However, this does not come up in my context, so don't like it. You can just think about cellular homology of CW complexes that are spaces. So some opportunities. Well, if we can have distinguishing between some things that look like S2 wedge S4 and CP2, well, we could, for example, use cohomology operations like the ring structure, or even if we're dealing with things like spectra, there's Steenrod squares, to obstruct a map from going from here to here, from this to this, that's an isomorphism on the fourth cohomology or fourth homology. In particular, these extra cohomological operations can really detect that we were gluing our cells together in a non-trivial way. And therefore, I said obstruct things that we might want to in our previous argument. Some challenges, well, for example, I mentioned we put U off to the side. There's not a single standard way to encode U or encode U and V. And this makes comparison of various theories or attempts to create theories for more difficult, and also just not deciding what category we're going to factor through and how we're encoding U in that context is a choice that there might be some choices that are better than others in different contexts. And also, if we add all this extra structure, but we don't have the computational tools to back that up, then we can't run the find obstructions, then show those obstructions actually matter. We can't run that second part of the theory. So some current examples, there's a stable homotopy for common homology. We're not dealing with common homology in this talk as much, but I include it because I think is one of the more successful in having those obstructions and computability. That there's also been Manolescu's S1 covariant stable homotopy type, which corresponds through a long chain of quasi-isomorphisms to Heegard-Fleur. There's also Manolescu and Sharkar's stable homotopy type that computes not Fleur for not specifically in S3, though we have a construction but not a proof for invariance yet to get that broader theory for obstructions up and running. And finally, what I'm going to be talking more about for the rest of this talk, there's lattice homotopy and not lattice homotopy. There's this where defined, it requires a certain construction for your three manifold or your not in order to get running. However, it does compute for some knots in three manifolds other than S3. So it's somewhere in between what's happening in these second and third points. It was developed by lattice homotopy was developed by Niemi as a three manifold invariant. Ozlas, Stipchitz, and Szabo created a construction for a chain complex that would play a similar role for not Fleur. And then some of my previous work was showing that chain complex and also the spacified version underneath it actually were invariants. So let's talk more about what those are. It takes in a certain input, it's that it requires a certain construction in the background. In particular, there's going to be a graph representing a plumbing of spheres. Here's my artistic representation of a disk bundle over a sphere. To do a plumbing, let me get blue, here. We'll take a D2 times D2 with aka a base, a D2 for the base and a B2 for the fiber in each sphere. And then we glue those together so that the disk bundle, the base of one becomes identified with the fiber of the other. And we then do that a bunch of times and encode it in a graph where the vertices are these disk bundles over spheres and the edges represent doing this plumbing operation. The adjacency matrix of this graph will read off the intersection form for the corresponding four manifold. And well, there are ways to talk about a lattice chain complex more generally. We're going to, for the spacified version, assume that it's negative definite. That's where it's been easiest to define and show invariance without relying on Heegard-Fleur and not Fleur's already results. And we also are going to assume, re-emphasizing my point from earlier, that our three manifold, the boundary of this four manifold, is a rational homology sphere. There's also the decoration of a spin-C structure in the background. This particular means that all of our surfaces we plumb together are spheres, and also our graph is a forest. So any cycle in our graph would create B1 for our boundary. So in that input, we get as output a filtered cube complex. In particular, there's a type function that we then look at super level sets for. So F0 in this case is these two vertices, because that's the only things that are bigger than or equal to 0 here. And if we go any higher than 0, we get nothing. F of -2 is the whole interval, and then anything lower than that is an interval. And this will be a invariant up to filtered homotopy for the pair three manifold plus spin-C decoration. And when we take persistent homology or the persistent chain complex, we'll get something that's quasi-isomorphic to the Heegard-Fleur. This proof works more generally than the negative definite case, but it assumes to do so completed coefficients. So we're using, this proof assumes power series coefficients. But the persistence complex, particularly in this case, each cell of our cube complex, each cube is going to give us a generator, and in particular of grading the dimension of the cell plus the height of the cell. And then the differential is the differential as a cube complex with powers of u inserted to keep track of differences in heights. And this is that bigger. Not lattice homotopy takes as input basically all the information we had before for the 3-manifold, plus an unweighted vertex to represent the new knot. In particular, if we just had a single disk bundle over a sphere, we could look at the boundary of the fiber, which will give you a knot in the 3-manifold bounding the disk bundle. And if we want to do this in a general plumbing, we then add an unweighted vertex adjacent to the vertex that it is a fiber of. In particular, you could see this edge as really representing the intersection of the 0 section with the fiber. This outputs a doubly filtered space, a doubly filtered cube complex, which is invariant for the knot in the 3-manifold with the spin C structure up to doubly filtered homotopy equivalents. And Brodziklu and Zemke showed for the persistent chain complex that computes knot Floer homology. They in fact did this for a broader case of links, but that has not been entirely specified yet. And as output, this is an example of a doubly filtered space. Instead of one height function, we have 2. And we then apply a similar process that is as before. We're using V's keep track of differences in the heights. This is a U because only the first one is differing. And this is a V because the second one of the heights is differing. So challenges and opportunities, particularly for lattice homotopy and not lattice homotopy. Some opportunities, it is combinatorial and explicit, which has been useful in computations, including already for Brieskorn spheres. It is also of interest to singularity theorists because this setup just means that there's a singularity in the background for some magical reason. And that means that we have people who are approaching this with who might notice different things and therefore be able to help us in ways that we wouldn't necessarily otherwise by ourselves, as low-dimensional topologists notice. It comes pre-specified. It also exhibits some symmetries that are similar to the involutive data on Haggard Floer and not Floer. I'll take a moment to jump to that part of the challenges and note that the part that is similar to the not involution behaves similarly in some respects, but is still slightly off. In particular, it is an actual involution. One of my conjectures is that this is a homogeneous portion of the not involution with respect to an extra grading that helps. That extra piece of data is not going to be graded with respect to this extra grading that lattice has. It also, for example, as an opportunity, provides a proof of concept for larger Floer homotopy results with regards to Haggard Floer and not Floer. However, as a challenge, while it provides a proof of concept, because it's not a full functor, you can't use the extra structure to obstruct cobordisms because we have not associated morphisms to every cobordism out there that we might care about. Furthermore, the presentation is still large enough that while it's explicit, we want to still be able to develop tools to work our way around it and be able to use those computational tools to find examples where the homotopy type really is actually distinguishing more than just the homology. And see you in the next talk.